today's goal of this lecture. Today I will see what is the identity theorem in complex analysis. Also I will see various type of exercise about identity theorem, because this topic is actually very important for higher study, also for any competitive exam. At first, see what is the identity theorem. Suppose f be the analytic function and m be the set of all zeros of the function f which has a limit point in the D, in the domain D. Then fz equal to 0. Zeros has where? In the domain D. Then that implies fz is identically 0 in the domain D. That means if the function is analytic, if f is analytic and M is the set which contain set of zeros of f. If set of zeros has a limit point in the domain D, here f defined from domain D to C. If it has a limit point in the domain D, then we can tell fz is identically equal to 0 in the domain D. Consequently, suppose fz is analytic in domain D. If a sequence Zn that converges to Z0 belongs to D such that Zn not equal to Z0 for any n belongs to natural number. Also, if Zn equal to 0, this is true for all n, then that implies fz equal to 0, identically equal to 0 on the domain D. That means if Zn converges to Z0, we all of us know by the criteria of continuity, fzn converges to fz0. If fzn equal to 0, fzn be the sequence which is equal to 0, then since fzn converges to fz0, then fz0 would be equal to 0, and since z0 is a arbitrary point, in the domain D, then that implies fz is identically equal to 0 on the domain D, and this is true for all z belongs to D. Okay, this is the sequentially criteria. Fz is identically equal to 0 on the domain D. Means first form of identity theorem is f defined from D to C and S which contain in the domain D such that S equal to Z belongs to C D such that Fz equal to 0. If S is the this set of zeros, and if S has a limit point in the domain D, then fz is identically 0 on the domain D. That means if set of zeros has a limit point in the domain D, then fz is identically equal to 0 on the domain D. As example, f be analytic function which is defined on the open disk complex C. Then f is constant if option 1 f of 1 over n equal to 0, this is true for n greater than equal to 1. Option 2 f of z equal to 0, and this is true for modulus of z equal to half. Option 3 f of 1 over n square equal to 0, and this is true for all n greater than equal to 1. Option 4 f of z equal to 0, and this is true for all z belongs to minus open interval minus 1 to 1. Notice option 1 f of 1 over n equal to 0. This is true for all n greater than equal to 1. Here n equal to z belongs to D such that fz equal to 0. And this is nothing but, this is since f of 1 over n equal to 0, this is actually the sequence 1 over n such that n belongs to natural number. This is the zeros of the set, and limit point of the set of zeros is f equal to 0, and which belongs to the domain D, because f be the analytic function defined on a open disk in C. F belongs to 0 belongs to the domain D, because this is belongs D equal to mod z less than 1. Hence, by identity theorem, f is identically equal to 0 on mod z less than 1. So, since f is identically equal to 0, that means f is constant. Next, fz equal to 0 for all z modulus of z equal to mod z equal to half. That means option B, fz equal to 0 for all mod z equal to half. Here the set of zeros is z belongs to D such that f of z equal to 0. And this is nothing but, this is z belongs to D such that modulus of z equal to half. On this set, this set is the zeros of the set, and limit point of the zero set means limit point contain n dash. This is obviously contain on the set mod z less than 1, because 0 here, if this is mod z less than 1, and if the set is, this is if the set is mod z equal to half, in this point the function contains 0. In this set function contains 0, and limit point would be whole mod z equal to half. So this is contain mod z less than 1, since limit point contain the zero set of limit point of the zero set is contained in the domain mod z less than 1. So by identity theorem we can tell f is identically equal to 0 on D, where D equal to mod z less than 1. Option 3, f of 1 over n square equal to 0 for all n greater than equal to 1. F of 1 over n square, this is same like first. Here n equal to set of 0 set is z belongs to domain such that f of z equal to 0. And this is nothing but this is 1 over n square, this set, at because f of 1 over n square equal to 0. This is nothing but 1 over n square where n belongs to natural number. So limit point of the 0 set is equal to 0, which is contained in mod z less than 1. So f is identically 0 in mod z less than 1 by identity theorem. And option 4, fz equal to 0 for all z belongs to minus 1 to 1. Here set of zeros contain consider this n. This is mod z less than 1, fz equal to 0. That means the set of 0 contain the set minus 1 to 1, and limit point which is contain n dash would be close interval minus 1 to 1, and this is n dash contain mod z less than 1, the set mod z less than 1. So by identity theorem fz is identically equal to 0 on mod z less than 1. So option 1, option 2, option 3 and option 4 are the right option. Next example, let f be analytic function in C, then f as constant if 0 set of the function contains the sequence n equal to 1 over n, an equal to minus 1 to the power n minus 1 times 1 over n, an equal to 1 over 2n. Option 4, an equal to n if 4 does not divide n, and 1 over n is if 4 divide n. Notice here function defined from complex number to complex number, and 0 set is set of those complex numbers such that fz equal to 0. 0 set, if in option 1 0 set contain the sequence 1 over n, and here an equal to 1 over n and limit an equal to 0. And since f be the function, analytic function in C, that means f be function from C to C, here limit an equal to 0, which be the member of C, so that imply fz equal to constant, and this is true for all z belongs to C. Option 2, an equal to minus 1 to the power n minus 1 times 1 over n. Here zeros of the set contain the sequence n equal to minus 1 to the power n minus 1 times 1 over n, where n belongs to natural number. This is contained in ZF. And limit of the zeros of the sequence is 0, which belongs to, here domain is C, F defined from C to C, which belongs to domain. So by identity theorem we can tell ZF is identically equal to 0, that imply Fz is constant. Option 3 also right option. Here ZF contain 1 over 2n and 1 over the sequence 1 over 2n tends to 0, which belongs to C. So this is right option. Option 4 also right. Here n equal to n when 4 does not divide n equal to 1 over n when 4 divided. Obviously this is also right option, because an contain a subsequence a4n which is equal to 1 over n if 4 divide n, and 1 over n goes to 0, which belongs to the complex number C. So by identity theorem Fz is identically equal to 0, which belongs to the complex number C. So by identity theorem Fz is also constant. So option 1, option 2, option 3, option 4 all are right option. Second form of identity theorem is, let f be a function from D to C and g be also function from D to C, which are both analytic on the domain D, and S be subset of D such that fz equal to gz. On this subset these two functions are coincide, and this is true for all z belongs to S. If S has a limit point, this subset has a limit point, if this limit point in the domain D, then we can tell fz is identically equal to gz on whole domain D. With such type Az equal to fz minus gz, which is analytic on the domain D, and the set S which contain the zeros of the set Az. Z belongs to D such that Az equal to 0. Since this subset S has a limit point in the domain D, so by identity theorem we can tell Az is identically equal to 0. That means we can tell by this fz is identically equal to gz. This is true for all z belongs to D. Example, consider f is entire function such that f of 1 over n equal to f of minus 1 over n equal to 1 over n. What is the cardinality of S? Here f of 1 over n equal to 1 over n. Consider 1 over n equal to z and g of z equal to z, and these two functions coincide in the set m equal to 1 over n such that n belongs to natural number, and limit point of the set m dash equal to 0, which contained in the complex number, because since f is entire function, that means f defined from complex to complex. Since limit point of the set belongs to domain, so we can tell fz equal to gz equal to z. That means fz equal to z. If we consider f of 1 over n equal to 1 over n, then fz equal to z I have got. But if we consider f of minus 1 over n equal to 1 over n, then consider minus 1 over n equal to z. That imply 1 over n equal to minus z. Then consider new function a is z equal to minus z and f of 1 over n equal to minus 1 over n. And these two functions coincide in the set n equal to 1 over n such that n belongs to natural number. And similarly, similar to before, this n limit of n this set is 0, which belongs to complex number. So f of z equal to h of z equal to minus z. That means f of z equal to minus z. Thing also would be included here. Given f is entire function and gz equal to z, this is also analytic on whole complex number. So here fz equal to gz, fz identically equal to gz, which is identically equal to gz on the whole complex number. Similarly, h of z is analytic on whole complex number. Okay, and fz is identically equal to h of z, which is identically equal to minus z on whole complex number. So fz equal to minus z. This is not possible. Here I have got f of z equal to z, and here also I have got f of z equal to minus z. This is cannot possible. So the cardinality is function s equal to f is entire function such that f of 1 over n equal to f of minus 1 over n equal to 1 over n square. Let f of 1 over n equal to 1 over n square. Take 1 over n equal to z. Then consider new function gz equal to z square. And notice these two functions are coincide on the set m equal to 1 over n such that n belongs to natural number. These two functions, since gz also is entered on since gz is analytic whole complex place, so gz is also entered. And notice the set m has a limit point m dash equal to 0, which belongs to complex plane. So we can tell fz equal to gz equal to z square. This is identically equal to, which is true on whole complex plane. Similarly, if we consider f of minus 1 over n equal to 1 over n square, f of minus 1 over n equal to 1 over n square, consider minus 1 over n equal to z. Then that implies, consider one new function gz equal to z square, and this is also entered on complex plane. Enter means this is analytic on complex plane. fz equal to z square, these two functions coincide on the set 1 over n. Here m equal to 1 over n such that n belongs to natural number. These two functions coincide on this set, and here m dash equal to limit point of the set is 0. So we can tell fz equal to gz equal to z square. This is true on whole complex plane. So this type of function can be exist. I hope my all viewers have understood this is okay. Well, today I will stop here. In my next video I will discuss more question about this identity theorem in complex analysis. Actually, identity theorem is very important for any competitive exam. Okay, See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.